For my talk, I'm very much going to follow something closer to Nick's talk. I'm here to talk about Alan. There will be a little bit of math, but I really want to focus on some stories, some of my experiences with Alan from a student perspective. I think you're allowed to stay. So the first time I encountered Alan, go ahead. I actually didn't even know it. As you learned from the last talk, he was mentioned in the preface of Peter Lax's linear algebra book, a book that I absolutely loved. And I remembered seeing the name of some high school student, and it was only after I encountered Alan at MIT that I remembered Alan is that high school student in my favorite linear algebra book. So that's why I knew the answer from the last talk immediately. And so for a little bit of background, I did my undergrad at Penn State, my undergrad and master's. And my thesis, what I worked on was multi-grid methods and spectral graph theory. And I get to MIT, I'm in my first year, and I'm looking at classes. So, my background is numerical linear algebra, numerical solution to elliptic PDE, so I start looking in the 18.3 category. And I'm looking at things and I say, oh, introduction to numerical methods, a nice grad class to refresh myself on numerical linear algebra, that sounds great. And then I get to eigenvalues of random matrices. And I can tell you this is going to sound strange. I had never really thought or truly heard of the idea of a random matrix before. And I thought, this sounds really interesting. This sounds really fascinating. Let me sign up for this class and see what eigenvalues of random matrices are all about. And I can tell you from the very first day of class, I could tell I was in for a class that was like no class I had ever taken before. So Alan has a set of notes for random matrix theory, which is and has been effectively, at least since 2016 when I took the course, it's effectively a book that has not yet been published as a book, I would say. This is one of the great sources of random matrix theory information. Anytime I forget something or I need something, this is the first place I go. And when you get these notes, when you get these notes, on the very first page, there's a preface. And this already gives you a sense of what you're in for. He says, begin with linear algebra, stir in some randomness, and watch the sparks fly. Mathematically, this is no surprise how many important areas have become even more interesting and more relevant by adding randomness. And at the heart of what I feel Alan's perspective on teaching random matrix theory and approach to sort of solving mathematic problems in general are really well summarized by this last little paragraph here. And I want to read this word for word because I think it's something really profound. He says, perhaps some mathematicians feel that once a theorem is proved, an experiment is unnecessary. Perhaps other mathematicians might say that an experiment is nice as a check, and a picture is fine if you can get one, but it's not terribly important. It is my hope that this book illustrates what many mathematicians already know. The more tools at your fingertips, the higher you can climb and the greater the view. So I already knew what I was in for. And right after the preface, before we even get to the first chapter, anything, we see an aside on the joy of random matrix experiments. Something that Alan certainly knows the thrills of. And this book was very much like his lectures. There was a focus and a real dedication to not just showing you a theorem and giving you the proof, but showing you, visually showing you and making you believe that something is fundamentally true, that you can see it, that you can feel it, and that you can understand why. We were at dinner last night, and I think all but one of us were all students who had taken 18.338, and I don't know what it was like when you all took it, but this was really the flavor of this class. And you can even see it, this is the first sort of thing you look at, and hold on, trying to get my slides to go, and the first chapter of the book gets you to the heart of things. 3 important distributions discovered at different times. The first page talks about the normal distribution. There is a picture. There is computation that shows you what this looks like and how you get it. And right after he introduces this to you, and he shows you the central limit theorem, what does he do? He tells you how to think about it. He tells you what it means, and he tells you the intuition behind this. And this is how he ran his class. And so I took this class the first year of my PhD, and this is something not quite like anything I had ever taken, and I had thought, wow, random matrix theory is really interesting. It's this very cool subject I had never really seen before. And I'm starting my PhD, and early on, I start working with Michelle, who was kind enough to come visit us in the audience today. So I start working with Michelle, and I'm working on things like determinantal point processes, some spectral graph theory, and Michelle becomes department head very soon after I start my PhD with him. And he's still department head, and he's quite busy. And so I'm working on these things, and near sort of like the end of like the 3rd year of my PhD, around 2019, I start working on some numerical linear algebra as well, and Michelle is helping me a lot, but also busy, and he suggests, John, why don't you go talk to some other people in the department that have expertise in this area? I think it could be really useful. And so I think, who should I talk to? Well, I remember this great random matrix theory class I took with Alan. And in fact, in the meantime, I guest lectured for 18.338 on determinantal point processes, something that Alan and I share as sort of a passion. And I could show you some math about determinantal point processes, but we're not here for math, we're here for Alan. Okay? So DPPs will have to wait. If you want to talk about it, talk to me after. So the title of this talk is 3 Years of Computing with Alan. So starting in 2020, and in fact, right before the pandemic, I start talking with Alan in person, and then all of a sudden the pandemic hits. And Alan, being the generous person he is willing to meet with me virtually every single week.
It's not generosity, I love it.
Okay. Is willing to meet with me virtually every single week to talk math. So we meet Saturday morning at 9 a.m. every single week since 2020. And we miss meetings occasionally when I'm, mid-flight, you're mid-flight, but we have meetings from hotel rooms, meetings from all sorts of strange places. My wife kindly asked that we skip the Saturday meeting right after my son was born, something that we granted her. And it's a reasonable request. And what did we talk about? Initially, we really didn't talk about a specific thing that we wanted to do research on. We were just talking about math. We were talking about things that we were interested in. We were trying to look into things, read different things that were interesting in determinantal point processes, things in quadrature, random matrix theory, orthogonal polynomials, and then we start getting into some numerical linear algebra. And we never knew at the start of our meeting, where is this hour going to take us? By the end, somehow, we're somewhere far away from where we started, but the journey is always sort of really worthwhile. And there's a space here because ideally there would be a picture of my thesis defense and Alan being present, but because of pandemic, this happened online. There is no picture of us together, and I don't think we thought to take a screenshot. But the main thing that I want to talk about, and the idea that I really want to hammer home, is that these 3 years of computing with Alan has really deeply impacted how I do mathematics. And I'd like to give you 3 examples, 2 of which are projects that are not with Alan, but have been really impacted by my interactions with Alan, and sort of respect for the power of computation, and then the third being work that Alan and I have finally gotten around to doing, specifically growth factor of Gaussian elimination under complete pivoting. So something that Alan has a long history with, and I feel like we have experts here, of course, but I pulled Alan back in, I might say. Okay, so example number 1. So this is a problem in spectral graph theory. So around near the end of my PhD, there was this open question in spectral graph theory that was really interesting to me. So if you're a graph theorist, take an adjacency matrix, or in general, you can take some symmetric, non-negative matrix. How far apart can its eigenvalues be? So this is something that's been well studied since the 60s, and specifically for the adjacency matrix of a graph. There was a very nice paper in 2001 where they proved a lot of results, and they made a couple conjectures. One about how big can this be for some fixed dimension, and the second being about what maximizes this for a fixed number of vertices and a fixed number of edges below the bipartite threshold. And so I'm visiting a friend of mine, so this is joint work with Jane Breen, Alex Riazanofsky, and Mike Tate. I'm visiting Mike. We actually managed to figure out the bipartite thing over a weekend, and then we keep talking about this general question, how far can these eigenvalues be? And using some typical spectral graph theory techniques, you do some averaging, you take some subgraph, replace it with an independent set with copies of some vertex. What you get out is you can prove with mathematical techniques that the optimizer has to look something like this. So the optimizer is a C matrix, as Nick Trefethen would say, or a graphon if you want to take n to infinity. And this graphon that solves this problem as you reach the continuum limit has to have this structure. It has to be 0 where there's white, 1s where there's black, and the size of these 7 blocks have to be some parameter. And you can prove this using some analytic techniques. But then we get stuck. We're trying, typical spectral graphic theory techniques. We're trying to come up with new techniques. This somehow should not be the answer. It really should be some 2x2 block that looks like this. With with 2/3 and 1/3. And so we're very stuck. We don't know what to do. But at the same time, I'm talking to Alan, and we're doing all these experiments, and we're drawing pictures. And we're looking to see the truth of something before we actually prove the truth of it. And so I think, you know what? Why don't I just draw a picture? And so I do some experiments for all the different step sizes you can have. And I say, what does the spread actually look like? And so I draw a picture. And what do you know? I notice the maximizer is on the boundary, and certain intervals really have to collapse. And then you collapse these intervals, and then again, the maximizer is on the boundary, and you get this sort of visual proof that this result is actually true. And so I show my collaborators, and they say, John, a picture's not a proof. This isn't quite right. And I say, well, I don't know. A picture is not far from a proof. And in fact, if you look at what's going on near these boundaries, the idea is that the set of equations that an optimizer has to satisfy can't all be simultaneously satisfied. You can plot pictures and you can see this is true. And so I say, I can see this with my eyes that this is clearly true. How do I turn this into a mathematical proof? Interval arithmetic, code this up, and it runs in under an hour, and it exactly tells you the truth of this answer. And this plot a picture, see the idea, understand why, and then just do it. This is something that, I inherited from Alan. Okay, example 2. This is from this year, and I get a kick out of this. So example 2, I'm working on some problem that involves some matrix factorization. And so some key step in this problem is I want to take any matrix from special linear group, and I need to factor it as the product of these, what I'll call block lower and upper triangular matrices. So I have A1, A2, A3, A4, A5, A6, and these are n by n matrices. These are n by n identity matrices, and I need to write any 2n by 2n matrix M as this product. And so I can prove that I can do this, and in fact, you really need 6 of these. You cannot do it with 5 for the special linear group or even a version for the general linear group. And the key workhorse was this really interesting result that might not be very well known, that if your n is not 2 and your field is, or your field is not GF2, it's not the field with 2 elements, then actually every element of the special linear group is a commutator of the general linear group. And this is like the key workhorse of this idea. But the problem is, well, you might say, what happens when n is 2? And what happens when this field is GF2? You have certain elements that are not commutators. So these are 3 examples. None of these are commutators of any 0, 1 matrices. You can check yourself. And so, I think of, the version of myself right during my undergrad or at the start of my master's thesis, I would have started doing, some test cases, really trying to work this out. And I really thought, wait a second, let me just check if this is actually true. This is a 2 by 2 matrix with 0, 1 entries. I can write code in Julia in about 10 minutes, and I can actually check if this result is true. And so I did. I wrote this up, and indeed, this result is still true even when you don't have this nice commutator structure. And I meet with Alan, and I show him this cool thing I did. I said, hey, look, there was this weird, pesky, GF2 n equals 2 case, and look, I coded some Julia code, and it just spit out the answer in about 5 seconds. How cool is that? And Alan said, whoa, that is really cool. But you know what? We could try to tweak this a little bit. We could try to, instead of writing it like this, have you thought of this idea? And we're meeting, and I just wanted to talk to him about this for 5 minutes. And by the end, we've spent well over an hour. And we're getting into sort of these deep questions of how to do this search optimally. And 5 seconds becomes 1 second. And I'm thoroughly impressed that Alan has managed to optimize this. And Alan says, no, we're not done. Alan says, let me send this to Valentin, who I am convinced is like one of the most impressive sort of computing people I've ever encountered. And Valentin manages to get this down. 1/3 of a second is pessimistic. I'll say on mine it's a 10th.
Valentin's a PhD student.
Valentin's a PhD student of Alan's, who, if you ever have code that you need to run, you think, oh, I need it to run 3 times as fast, give it to Valentin and it will come back 10 times as fast. Yes.
And that's after you've convinced there's no more room left.
After I was already convinced, Alan, this thing, there's no way we can speed this thing up. How is it going to happen? Yes.
He's right on the other side of that.
He's probably on the other side of the board. But the idea of trying to take some problem and doing it the best way possible and trying to get to the heart of what is the best way we can do this. 1/10 of a second versus 5 might not matter for this problem, but for the next person who's trying to do something like this with Julia, Alan, Valentin, we know how to do this in an optimized way. Okay. And finally, now I want to get into, with the little bit of time I have left, the heart of the question that Alan and I started to converge upon when we started talking more and more. And this is this growth factor and Gaussian elimination problem. So you have some matrix A, you permute it with permutation matrices P and Q, and you want to write this as the product L times U. And the idea is you would like the entries of L and U not to be too big compared to the entries of A, because, well, standard sort of results about stability tell you that this is governed by condition number of A, growth factor, and number of length of your mantissa. And okay, and so we started studying this question for complete pivoting. And there's this old bound due to Wilkinson that says the growth factor under complete pivoting is like an upper bound of 2 times n to the log n over 4. You get this by taking Hadamard's inequality a bunch of times, converting this to an LP, getting a dual and sort of guessing. He doesn't say LP in his proof, but this is roughly what he's doing, getting some dual, and then this pops out. Okay. And there was this old conjecture, kind of a folklore type conjecture from the 60s. Some people attributed it to Cryer, some people called it Wilkinson's conjecture himself from papers back then, but maybe it seems no one actually conjectured it, it was in the air. And they conjectured that the growth factor for a real n by n matrix under complete pivoting is at most n, which was a reasonable conjecture at the time. You take a Hadamard matrix, you do Gaussian elimination under complete pivoting, you get n out. They say real because even back then, just by taking a 3 by 3 matrix, you can see that for a complex matrix, this is not true. Okay. Well, the 90s come along, and Nick Gould is doing some experiments in Lancelot, and he finds a 13 by 13 matrix that has ever so slightly a larger growth factor than 13. And in fact, he found a couple examples for other small values. And Alan comes a year later and figures out that no, this is not just a growth factor in floating point arithmetic, this is an example in exact arithmetic, that this threshold has been broken.
A little bit of tweaking of the numbers is necessary.
Yes, and that the exact matrix itself did not suffice. He had to actually change the matrix, which is a very good point for what I'm about to get to. So there's this question still, what is the maximum growth? How does this scale with n for complete pivoting? For partial pivoting, this is well known to be 2 to the n minus 1. Okay. And so Alan and I together, we managed to not only show that this old conjecture is false for a couple values, but in fact, it's false for all n at least 11, and it's off by a multiplicative constant. And the way we did this really is through computing and by taking a computational trick and sort of making it a theoretical one. And so the idea is, the way that we managed to see this is by numerically searching and computing matrices with large growth using JMP. Then we use mathematical sort of theorems, which are sort of a version of an algorithm with provable guarantees that tell you if you have a computed matrix that has some large growth factor in floating point arithmetic, that there's actually an algorithmic technique you can do to take that matrix and convert it to one that has large growth factor under exact arithmetic. So functionally doing what Alan did in his 92 paper, but doing this algorithmically with mathematical guarantees. And then you have things with guaranteed large growth factor, and now you can use extrapolation results to take large growth for sufficiently large bands that are fairly small but large, and to convert these to guarantees for all n. And so, for instance, here's a large chart of computed growth factors all the way up to 75 and an extra one at 100. Yeah. And with the last couple minutes, I don't want to hold you from coffee and break too much, but recently, Alan said, okay, this is great what we're doing. Wouldn't it be great if we got more people involved? Why should we have all the fun? And so Alan had this great idea. Why don't we reach out to Yufei Zhao in our math department and see if there's any undergrads who are into matrices who might have some fun with us. And Yufei says, yeah, Alan, John, I have this great undergrad. His name is Ankit. And we've been working with Ankit, a very, very talented undergrad, for the past about a year and a half. He's now going to be a rising junior, and we've been asking questions about this upper bound. So we've moved this lower bound, and this old upper bound, everyone believes this must be pessimistic. Hadamard's inequality can't be tight everywhere. It's just not possible. And so we took this intuition to actually build a proof that says, no, you can actually decrease this exponential constant in Wilkinson's bound. And this is in preparation, hopefully should be written up and on the archive this month, and Alan was interested in us talking about this and presenting this, but the big idea is that you can prove technical lemmas that say I have some matrix, I add another low rank matrix. The determinant of what I get at the end really shouldn't be like the determinant of a Hadamard matrix, because it's of a really different flavor. And so you prove things like this, and these give you extra bounds and extra constraints. And then all of a sudden you get some nonlinear optimization problem. And what do you know? We go back to computation, and through numerical insights from the JUMP nonlinear optimization Julia software, we can actually see asymptotically, what do these nonlinear optimization problems behave like? Where are they tight? And this allows us to asymptotically, intelligently guess things about the dual, understand the ways in which we can relax it without losing anything. And this gives us an improved bound. Okay, I have one more minute before 10:30, and I want to leave you with one last thought. And this is probably one of the most interesting conversations I've had with Alan, so I want to end with this conversation. So I'm talking to Alan one Saturday morning. We're talking about some algorithmic technique to compute something. And I'm saying, let's do something a certain way. And he's saying, John, why are you doing it that way? And I tell him, I'm doing it this way because this is what I can prove. I do it this way because I do this technique and I get a provable guarantee at the end. And Alan says, John, you can ignore the advice I'm about to give you, which means this is advice I really should listen to. And he says, some mathematicians, they have a problem and they know their problem is across the street. But they hang out on the other side of the street because there's a lamppost there and there's light there. Because they know what they can do there. They know how to do things there.
I can invent this analogy.
Okay, but this was the first I heard it, and it was great. And he said, you know, some people do this and that's fine, but what's really great is to find a problem and go exactly where that problem is. Why spend your time across the street at the lamppost with the techniques you know, when you can get to the heart of the problem and live there? And the main takeaway that I've gotten from working with Alan, to put back up his own words and then to put a paraphrase of how I think Alan often thinks, is Alan, when he encounters a problem, he always wants to meet it at the source. And oftentimes, when you're meeting a problem at the source, computation is the first step. All right. And that's my talk. I'll release you all to coffee. Thank you.
That was wonderful. I want to say two things quickly. The first is, of course, I believe in this philosophy, and I hope some of you have read my Applied Mathematician's Apology, which is very much about how mathematics can come from computation. The other thing I wanted to mention, I'm probably the only person in the room who has heard Wilkinson talk about his upper bound. Anyone else? Right, so I remember that, and he gave a great talk. He was a great speaker, and he said back in 1961 when they proved that, they figured, well, this was an obvious, very weak bound, next week we'll improve on it. And here we are, what is it, 52 years later, and finally you're improving on it. That's incredible. Sorry, 68, right, I should be a mathematician. Thank you.
Yes, thank you.
Any more comments?
I could say this whole philosophy is probably not mine, but I learned it from Nick, and I think this whole philosophy is probably I picked up from Nick, and I think I've noticed not only all of Nick's students, but I think all of his grand students have that philosophy. Yeah.
So let's thank John again.